Our next speaker is Professor Sebastian Wieczorek. He is the chair of the Department of Applied Mathematics in the University of College Cork, Ireland. And he works mostly on the stability of non-autonomous dynamical systems. And he is one of the leading experts in the area of rate-dependent tipping. Hope you will enjoy his lecture a lot. Thank you. You can start.
Yeah, thank you very much. Welcome, everyone. And thank you for the nice introduction. So what I will do today is I will give a very short lecture about a very simple example that has both types of tipping points, bifurcation-induced tipping points, which we call B-tipping in short, and rate-induced tipping points, which we call R-tipping in short. And the idea here is to give you a bit of a feeling how these different tipping mechanisms come about in very simple dynamical systems. So I'm actually going to work out through a very simple equation, do simple bifurcation analysis, and maybe explain the difference and the challenges if you want to look at stability of systems with external inputs and the difference between autonomous and non-autonomous systems. So this example that I'm going to discuss today, it's an example from this paper right there that we published with Pete Ashwin, Renato Vitola, and Peter Cox in 2012. Tipping points in open systems. I will be talking about tipping points in open system. And this is one of the simple examples, one of the first examples that we have in this paper. I will just work it out in more details here. And before I go ahead with this simple example, I would like to maybe set the scene and discuss the setting of the whole problem of tipping points. And this setting is going to have two parts. The first part is the mathematical viewpoint. And the mathematical viewpoint is that we're looking at dynamical systems, and there are different types of dynamical systems. And one way of categorizing dynamical systems would be to divide them into continuous time dynamical systems and discrete time dynamical systems. So for continuous time, you have examples such as ordinary differential equations or ODEs or partial differential equations. Things change continuously over time. And for discrete, you have maps of this sort. So one example would be a logistic map. Okay? Now I'm going to focus entirely on continuous time dynamical systems and tipping in this type of systems. And within this category, you can again have a lot of different classifications. And the important classification for today is that you can divide them into autonomous and non-autonomous. So this is an example of an autonomous dynamical system. And you see that the right-hand side does not depend explicitly on time. I mean, X, of course, varies over time, but there is no time dependence other than through X. Okay? And then we say the system is autonomous. Now, in contrast, non-autonomous dynamical system will have explicit dependence on time t in addition to the time dependence of X. Now, we know quite a lot about autonomous dynamical systems and stability for those systems. And the reason for that is that they have compact invariant sets in their phase space, such as equilibrium, limit cycle, tori, chaotic attractors. And you can linearize about those invariant sets and, say a few things about local stability. Sometimes you can talk about global stability, but in general, there is a very well-established theory, which is called classical bifurcation theory for autonomous dynamical systems that allows us to study stability, changes of stability in these systems as you vary some parameter. Now, this is not the case for non-autonomous dynamical system, and the main challenge or the main obstacle would be that such systems don't have compact invariant sets. So equilibria, limit cycles, or tori do not exist in the phase space of a non-autonomous system. Sometimes you can do an extension of the phase space and it still will be a problem. Okay? Instead, people sort of ask what are the natural objects to look at in such systems. And mathematicians come up with these ideas, pullback attractors and pullback repellers. You could have pullback saddle trajectories. I'm not going to spend too much time talking about what they are and formal definitions, but I will have some examples here. So the main problem is that if you ask about bifurcation theory for non-autonomous dynamical systems, then many people would agree there isn't a well-established bifurcation theory. Pullback attractors say will be a good natural starting point, but as I will explain later, that doesn't always work for tipping either. Okay, so there is some ideas here, and they are of course very, very useful, and they can give you the full solution in certain examples, but in general, I think we don't have something that works very well and would address all examples. So this is the mathematical viewpoint. This is where we live. We're going to be talking about this autonomous versus non-autonomous simple example. And then I'm going to give some perspective from the science viewpoint. Okay? In science, when you construct mathematical models, you model what we call open systems. So every system is open to external disturbances. And open systems is nothing else as dynamical systems that are subject to some time-varying inputs. And this time-varying input, I'm going to denote it with lambda of t here throughout my talk. So the first thing you notice that any forced system that is subject to a force that comes, or an input that comes from the outside of the outside world, would be non-autonomous because it has this explicit time dependence of that input. Okay, so immediately you're sort of moving away from this situation where you have this classical bifurcation theory. You're moving into this mathematical setting here. So there is a bit of a challenge here for studying tipping points, and that's why we are sort of giving these talks here in the workshop. And when you look at the system, you have x dot equals f of x lambda of t. Lambda varies over time, usually very, very slowly, and usually not by much. And you're interested in these instabilities or bifurcations, if you will, and we call them tipping points. So the sudden transitions from what we call a base state. You identify some state of that system, which is usually desired. It's your base state. And as lambda varies over time, we have this sudden transition from a base state to some other state, which we call alternative state. And now there are different types of alternative states. Alternative stable states, this is something people may be used to quite a lot, but there are also alternative states which need not be stable in the sense they can be metastable. Like you can go there, you can spend there some time, could be long, shorter, but it's finite, and then you return back to the base state. So there could be tipping points which sort of go somewhere else for good and stay for all remaining time in alternative stable state. But it could be tipping points in excitable systems where you sort of move away from the base state, you go to some alternative metastable state, and then you return back to the base state after some time. So a number of possibilities can occur here. And we call it, Pete Ashwin and I would call it reversible and irreversible tipping points. And people come up with different names here, but this is just to give you a taste that there are sort of different possibilities that can occur in those systems. Now, my approach in my research and in this simple sort of tutorial will be that I would like to relate solutions of this non-autonomous system to solutions and equilibria of the frozen system. And the frozen system is an equivalent system when lambda does not vary over time, but it's fixed. And you just look at the system for different but fixed values of the input parameter lambda. So I remove the time dependence. I just consider different lambdas, and I solve for equilibria, and I can do bifurcation stability because I'm now in the autonomous dynamical system setting. And I use this as a reference for what happens when lambda varies slowly. Okay, so that's going to be the main idea of the talk. And this is the simple example. Okay. This is from section 3A of this paper, which I just described. And I look at this non-autonomous system right here. So you see this is a modified saddle node normal form. Okay. So x dot is equal to x plus lambda 1 of RT. This is all squared minus lambda 2 of RT. Now what it means that my input has two parameters, lambda 1 and lambda 2. You can think of a two-dimensional input, and they both can vary over time. What I will do, I will vary one of them over time at a time. So I'll fix one of them, vary the other, and then I'm going to vary this one and fix the other one. Okay? When I talk about the frozen system, what I mean It's a system when both of these inputs become fixed in time parameters. And that's an example of the frozen system. Lambda 1 and lambda 2 are just input parameters. So here's my non-autonomous system, and this is the corresponding frozen autonomous system right there. And what I want to do really, I want to just look at some analysis of that frozen system. And the best point to start is always to look at equilibrium solutions. And you look at the equilibrium by setting this derivative to 0. So I'm going to say 0 equals, and I'm going to rewrite it slightly differently. I'm going to use xe for x to denote that I'm looking for equilibrium solutions. I'm going to have xe plus lambda 1 minus root lambda 2 times xe plus lambda 1 plus root lambda 2. It's just a different way of rewriting this as a product. And this is 0 and either of the brackets is 0, so that gives me two equilibrium solutions. Okay, and I'm going to call them xe1, which is equal to minus lambda 1 plus root lambda 2. And I'm going to have xe2, which is equal to negative lambda 1 minus root of lambda 2. Okay, so now these are two equilibrium solutions. You see, they don't always exist, okay, because that will depend on the sign of lambda 2. I have a root of lambda 2. And I can immediately say that there's three possibilities. I have two equilibria when lambda 2 is greater than 0. One equilibrium when lambda 2 equals 0. So this is a degenerate situation when xe1 equals xe2 equals negative lambda 1. And I have 0 or no equilibrium when lambda 2 is negative. Okay, so that's a sort of indication of a saddle node bifurcation here. Now I'd like to get very quickly stability information on these things. I know that can be very simple and boring for a number of people, but it's important for me to go through these steps to sort of indicate how we deal with the non-autonomous equivalent. Okay, so look at stability. So I'm gonna go back here to this equation for a moment. I'm going to call it f of x. Okay, and I get stability of my equilibria from f prime of x, okay, which is equal to 2x plus lambda 1. Okay, and I can check that f prime of xe1 equals 2. Now, if I substitute xe1 here, I have negative lambda 1 plus lambda 1. I'm going to have root lambda 2. And I'm going to check f prime at xe2. So I'm going to plug this here. Lambda drops out and have negative 2 lambda 2. Okay, so what I have is the situation where this xe1 is unstable. And xe2 is stable. Because this is negative and this is positive. Okay, so I now know the stability, and I can sketch a very simple bifurcation diagram, okay, for the system as a function of lambda 2. So let's just do it and see what's going on. If I'm going to fix lambda 1 now, so set lambda 1 equals to 0 for simplicity, I'm going to sketch the bifurcation diagram. It's a one parameter bifurcation diagram when I'm going to vary lambda 2 here. So this is my bifurcation point. Okay, and I'm going to have two solutions. Let's just see. The one which is above is going to be unstable. The one which is below is going to be stable. So I have a square root behavior like in lambda 2. So this is what I'm drawing. Okay. This is my bifurcation diagram. I have two branches, stable branch of equilibrium, unstable branch of equilibrium. They bifurcate, and for when lambda is negative, there is no solutions. Okay. So this is one way of looking at the problem. But I'm also going to have a look at this problem from a different perspective when I fix lambda 2 and I vary lambda 1, just to give an idea of what's going on. Okay. Now this is going to be lambda 1. This is my xe, and I fix lambda 1 to 0. I'm going to fix lambda 2 to 1. Okay. So I'm going to have these two situations at 1 and -1. So just bear with me. I'm going to tilt it a little bit to do a nice job here, plotting these two branches of equilibrium. Okay, there we go. Okay, now let's just maybe give them names. So the one above would be xe1. This is xe2. And this is xe2, xe1. Now you have a bit of a feeling of what's going on in this system if you want to play around with the parameters, okay? Either lambda 2 or lambda 1. Now, if you look at this situation, okay, so then just see, yeah. If you look at this situation, okay, you see that obviously if I'm going to vary lambda 2, you know that funny things are going to happen, because if lambda 2 increases over time very slowly, you're going to follow this branch of stable equilibrium points. You get to that saddle node bifurcation. There is no stable point to follow or track, and you're going to move to some other state. Okay, just going to move away from your base state here. So this is intuitively clear what happens when you start varying that parameter lambda 2 slowly over time. It's maybe less intuitive on the right-hand side when you start to vary lambda 1 over time. Okay, because what happens for every fixed and static value of lambda 1, you have the same situation, which is a stable base state, this xe2, that never bifurcates, it never disappears, it never loses stability. So it is always there. What it means that in practice, you should sort of expect intuitively that if you go slowly enough, nothing will happen in the system. But what you can see from that plot is that if you maybe go a bit too fast, you can expect some instabilities or bifurcations. However, this will be genuine or pure non-autonomous instabilities or bifurcations because the underlying frozen system does not have any bifurcations. Okay, and that's sort of the main sort of idea behind rate-induced tipping. You look at the frozen system and the bifurcation diagram of the frozen system, there is no indication of bifurcation or instability whatsoever based on the frozen system, looking at different but fixed in time values of the parameter. Yet, when that parameter varies over time, you're going to have an instability. And then the question is, how do you capture this? Because the moment you vary lambda 1 over time, okay, then you have a non-autonomous system and you can't just do what I did. You can't linearize about an equilibrium because that system does not have any equilibrium solutions. Okay, so let me just go through these two simple examples. I'm going to very briefly describe this and do some more calculations on the rate-induced tipping, simple calculations to show you how this rate-induced tipping comes about and how you can actually, in that simple example, capture it analytically. Okay. So there we go. This is the simple example that people have seen many times. Now, let me see if I have another color here. I think that will have to do. So say I start somewhere here close to. Now I have them slightly wrong way around. So this is xe1, xe2. Yeah, that's correct now. Now, if I start from some initial condition here and I decrease lambda 2 very slowly over time, so very slowly means much slower than the internal dynamics of this system. So I have a quick approach towards this equilibrium. It's quick. Then I'm going to follow that equilibrium. I'm going to lag behind a little bit all the time because that thing is moving over time and I'm trying to catch up with the moving moving equilibrium. It's going to continue all the way here, slowly. And then at this point, a slight overshoot, and then I'm going to move away to some other distant state. I'm going to tip. And this is what we call bifurcation-induced tipping, and that's the obvious thing. You can understand it entirely based on the bifurcation analysis of the frozen system. Okay, now that's a simple example. You see the same dynamical systems is varying a different parameter here. Let's now go to the other situation, and this is just to recall. Now my lambda1 is a function of time, and I make it a very simple function of time. It's going to be equal to RT. What it means is that lambda changes linearly over time at a rate R. It's a ramp with a slope R. Okay, so it doesn't start anywhere, doesn't end anywhere, it just keeps increasing linearly. So that's a bit of a limitation, but it's a simple situation that we can handle. And I'm going to fix lambda2 to equals 1. This is exactly what we had just a moment ago. Now the resulting problem is this non-autonomous dynamical system. Okay, and then I can now again look at the corresponding bifurcation diagram of a system like that when I freeze lambda1, and this is what I have. Okay, so I'm now going to increase lambda1 from some point here to some point there. See, if you increase very slowly, nothing can possibly happen. But if you were to increase instantaneously, so you start at this value here of the stable equilibrium, and you have an instantaneous jump in lambda1 from this value to some value here. So that jump means that you change the dynamical system instantaneously, and you use this state as an initial condition for the new value of lambda1. So if you hear lambda1 is fixed to that value, and then you instantaneously switch lambda to a value here, then this old state becomes your new initial condition. You are above the unstable equilibrium and you're going to tip. So you see, this is the situation. I'm going to maybe sketch this here. At some initial value lambda, let's call it lambda negative, okay, I'm going to be here. So I'm going to have xe2 of lambda negative, okay, and I'm going to be a happy camper. I'm at a stable equilibrium. But now lambda in the system changes. If lambda changes very slowly, you expect to stay close to that stable moving equilibrium. But if lambda changes instantaneously to some value, and then you know that that value has to be greater than what you get here. So say to some value which is there, lambda plus, okay. Then what you have is that this xe2 at lambda negative is outside of the basin of attraction of xe2 at lambda positive. Okay, so this guy is no longer in the basin of attraction of xe2 at lambda positive. It's in the basin of attraction of some other attractor, and the system will move towards that other attractor. Okay, so now if I go extremely slowly, I have tracking, nothing happens. If I go infinitely fast, I have this tipping. So that means that there is at least one finite value of the rate R that will give me a transition from tracking to tipping. And I would like to find out what it is. Okay, and in this simple example, because I constructed it so, it is possible to actually find out what that value is. Now, the way I'm going to go about this, it's still not sort of non-trivial. I'm going to go to a co-moving frame. And you see there's a number of special things about this example. The ramp is linear, and this equation has a very special form that the dependence on x always comes such that I have x plus rt. Okay, I never have rt on its own, and I never have x on its own. And that's by design, so I can do the trick that I'm going to do right now. So I'm going to introduce a co-moving frame or a moving frame. Variable, and this is going to be y equals x plus rt. And I'm going to rewrite this equation for an equation for y. So y dot would be equal to x dot plus r, okay, and this is exactly what you see here. And now my x dot from equation there is x plus rt, which is y squared, plus r. Okay, so in the moving frame, okay, in the moving frame at the rate r, I got an autonomous system. So now I can solve for equilibrium of this system, and that's actually relatively straightforward, right? So that's what I can do easily. So y e1 would be equal minus root r, y e2 would be equal plus root r, okay? And let me just check that what I'm doing is all right here. A little bit. Yeah, so there's something, I missed something here, I think. Oh yeah, so I think I missed something. Yes, I missed this one, haven't I? Yeah, that's why it doesn't make sense. Okay, I have -1 here. There we go. So yeah, dot is this y squared -1 plus r. I think this is okay now. So I'm gonna have it slightly different, you know. Okay. Now my y e1 is equal minus root of r -1. My y e2 is equal plus root of r -1. Okay, there we go. I think got it right this time. So I have two equilibria in the moving frame, and this equilibria correspond to invariant lines for x of t. Okay. So now I'm going to have x1. Now I'm going to this relation back. So x1 would be y1 minus rt minus root of r -1 minus rt. And the second line x2 is equal plus root of r -1 minus rt. Okay, and now what happens? I can check stability of this equilibria. Okay, for e1, y e1 and y e2, and you can do it very easily. Okay, so you get this. The first one is stable. This one is unstable for y, and that means that this line is a stable attracting line, and this line is an unstable attracting line. And in other words, this is a pullback attractor. It's a line that attracts, and this is a pullback repeller. Okay, now if I look at this very, very closely, I can also distinguish three situations here. Okay. If R is always positive, just to avoid confusion. Okay, if my R is between 0 and 1, then this square root is defined, and there are two invariant lines. Okay, now there's a special situation here. If R equals 1, there is just one invariant line. Okay, because if R equals 1, x1 is equal to x2, and this is equal to negative RT. Okay, so maybe to be more precise, whereas I'm going to indicate that while these are equilibrium solutions, these two solutions are time dependent. So I have x1 of t And I have also x2 of t. Okay, so this is sort of in the plane x lambda 1, there will be lines, or in the plane x times versus time, that will also be lines. And there's a third case, that if r is greater than 1, okay, then the square root is not defined, neither of these exists. There are no invariant lines. So obviously something happens with those invariant lines. And what happens here is that as r increases, okay, these frozen lines of equilibria, they perturb to a pullback attractor and a pullback repeller. And this pullback attractor and the pullback repeller, they approach each other and they collide in a saddle node bifurcation of these pullback objects. And this happens when r equals exactly 1, and that's my critical rate. So this is some RC, my critical rate. When R exceeds this critical rate, then I lose both pullback attractor and a pullback repeller. So most importantly, I don't have a pullback attractor, something that I can converge to, and the system diverges away and tips. And notice that all this happens when you just move too fast. It only depends on how fast you move, on the rate of the movement. And because I set up my example in such a nice and easy way, I was actually able to obtain this result analytically on half a page. I would like to now draft of what's going on here. So this is now, I just don't want to confuse. So you probably have it the wrong way around again. Yes, I think this is xe1. This is xe2. I'm going to look at three situations. First, so this is the frozen system. Now I vary lambda 1 over time, and I see what happens to the frozen system. And I vary it slowly, and by slowly I mean that r is between 0 and 1. Okay, this is what slow means. So what you actually get, you get these two invariant lines that like so. So there's one which is a pullback repeller, which is here, and a pullback attractor, which is there. So you see, for a small r, these two things perturb. The line of repelling equilibrium perturbs to this pullback repeller. The line of attracting equilibrium perturbs to this pullback attractor. And if you start with some initial condition right there, you're going to be just attracted to this line, and you're going to move along this line. And you keep on moving because your lambda 1 moves over time. Remember, it increases over time. Okay, this is the setup. If you now start close to the pullback repeller, you're going to be repelled from there and attracted towards the attractor. And then you keep on moving. Now, if you start on the other side, it's going to diverge. Okay? So now we have this situation, which is just a perturbation of the static system. And that's what you expect from the differential theory. Okay, that normally hyperbolic slow manifolds persist, and that's just a different way of saying this. Now we were able to actually obtain formulas for that. Now, a funny thing happens when r equals 1. Because these two, pullback repeller and attractor, they collide. I'm going to draw this guy in the middle in red. So there's only one of those guys. I should also put arrows here because the flow on these goes. So now these two come closer, and they collide to a single one. Okay, so now this is that critical rate situation where if you start, you're going to approach this one from below, but you're going to move away from it from above. It's like a neutrally stable or non-hyperbolic pullback object. Okay, so non-hyperbolic pullback object. So you see, you attract from below and you repel from above. Now, when R becomes, so that's a critical rate situation. And when you go higher up, everything disappears. Okay, so what you have a trajectory that sort of goes like this and like that, and it tips. And all trajectories just move away to infinity. So the important point here is that if R very slowly enough, of course, Fenchel theorem is true, and then you can find close to the frozen system equilibria, you can find those pullback attractors and pullback repellers. You can find trajectories that stay close enough, and everything is all right. It's just a simple perturbation of the frozen system. However, there are many systems, and when we started looking around, it turns out that most of the systems that people study have this property that when you change at the higher rate, things go wrong. Okay, and that can be obvious or non-obvious, but usually there's this critical rates, and what that sort of represents here is that these perturbations of the static solutions, they actually collide and disappear. So you have static solutions, but the solution for the non-autonomous system now has nothing to do with the static solutions. It's far away from them. This is an unstable and stable solution. This guy is neither. So it really starts to differ. And when the rate is too high, and I say R greater than 1, you have static frozen solutions, but the non-autonomous system doesn't have any solutions nearby. The solution of the non-autonomous system has nothing to do with it because the non-autonomous system has undergone this non-autonomous instability here. Okay, so maybe at this point, I'm going to sort of pause for a second and ask if people have any questions maybe about what I just described. And I'm going to say a few things about how to generalize what I just described. Right, no questions?
Can you hear me? Hi, can you hear me?
Yes.
I only had one small comment. I think in the equilibrium solutions of the moving frame, within the square root, it must have been 1 minus R. I think the sign was flipped, but otherwise, I just
okay, so hold on, let's go. So this is, have page 4 is here. Oh, you mean here?
Yes,
That's right. Yeah. Sorry. This is the problem when you try to do things in real time. I just have too many pages floating around. So yeah. So let's just do that right. Minus, yeah.
There's one
Thank
more
you so much.
We'll pass on the mic.
Yeah. Sorry?
Sir, I want to ask that in the case of R greater than RC, like the greater than 1 actually, so there is no solution in this case for the non-autonomous system, though, so that for any initial condition, the trajectory will be moving around in time for a certain period, and then will it return back to some attractor? Like, is it there permanently?
Yes. Okay. So in this simple system, right, that I'm doing, there's only one attractor, which is this, and in the frozen system that. And if you noted that attractor, then you have this repelling solution, and on the other side of the repelling solution, you go to infinity. And this is just a simple example that I have. But in typical systems from applications, you would have more than one attractor, and you wouldn't diverge to infinity. You would just go to another attractor. Okay. So in this situation here, everything below that dashed red line goes towards the blue line. This blue line is an attracting line. Everything initiated above the red line will diverge to infinity. So my alternative stable state is infinity, and it never comes back. It goes there and stays there for good. Okay, it never comes back in this simple example.
Okay.
So now, if I go to this situation, everything from below the red line will approach the red line. Everything from above goes to infinity and never comes back. Now, for this case that you've asked about, any initial condition will lead to a trajectory that goes to infinity and never comes back.
Okay, thank you.
And any other questions? All right, so maybe what I'll just say a few things. That's a very simple toy example. Okay, that's something that you can sit down and repeat yourself without the typos and little mistakes, and convince yourself how simple rate-induced tipping comes about. Okay, I think it's a sort of very pedagogical example to go through if you're interested in this rate-induced tipping phenomena. Now, if the system is higher dimensional, what you can have, and it's excitable, what you can have is that you sort of, like here, you move away from your base state, and then eventually you come back, okay, to the base state. So you don't always go and stay away for good or forever. Now, even more interesting examples are that here we have this very obvious R-tipping threshold, which is this unstable line. You know that when you cross this unstable line, you're going to have tipping and so on. But there are some systems, again, excitable systems, that don't have unique thresholds. They have quasi-thresholds. If you, for example, look at the simple neuron model Fitzhugh-Nagumo, it's a slow, fast model with slow manifolds. And instead of a uniquely defined threshold, there is a non-unique threshold, which has to do with canard trajectories following some slow manifold of a slow, fast system. Now, I don't know whether people are familiar with the slow, fast system theory, but that would be one example, at least for those who are familiar. Now, I don't have that example here. What I want to talk about here is what happens when you don't have that very nice and simple situation that I had here. So I manufactured that example, for you, where I could do it on a piece of paper. But generally, the input is not a linear ramp, can be nonlinear. It can vary in a very complicated way. And can I do something similar to what I just have done for arbitrary inputs? So this is where the main problem lies with non-autonomous system. And the answer is that when the input is arbitrary, we don't have a good theory to deal with this type of problems. However, there is a class of inputs which allow complicated time variation, and they give us a way of handling these problems in a slightly different way. Okay? And this type of inputs I'm going to describe in my research talk next week, but I'm just going to give you a bit of an idea. Okay, here. So these are inputs what we call asymptotically constant inputs. So what I have, I'm going to sketch one, or maybe just okay. So I'm going to maybe write. If I send time to positive and negative infinity, and I look at my lambda of t, I want it to go to some constants, lambda plus minus. And I also want the derivative of lambda to be 0. So I'm looking at inputs that can be as complicated as you wish for finite time, but in the past and in the future, they sort of die out to a constant. In other words, you're looking at inputs that they start somewhere, they do some variation, and then eventually they stop somewhere else, or maybe the same value. It doesn't matter. So here are some examples of such inputs. Okay, so you can have a simple example would be an impulse like that. So this is lambda of t. This is t. Okay. Even a simpler example would be maybe a nonlinear switch that goes from one constant value here, lambda minus, to another lambda plus. But these are simple examples of a monotone and non-monotone. So for example, hyperbolic tangent and hyperbolic secant. But if you look at more general situation, you can have something which is actually quite complicated. You could have something which is maybe semi-chaotic, and then it sort of dies out here and dies out there, sorry, to a constant, okay, as time goes to infinity. So this type of inputs are promising, and we know how to handle them. because as time goes to positive and negative infinities, they settle down to a constant value. Okay, so for these inputs, we have an approach which we call a special type of compactification. And this is something that Pete Ashwin will mention in his talk next week. And this is something that I will describe in my talk next week as well. So in this type of inputs, we sort of compactify this extra dimension onto a compact interval, -1, +1, and then you can analyze R-tipping. You turn the non-autonomous system, that's an important thing, okay? So we use compactification. To turn a non-autonomous system into an autonomous system. Plus one extra dimension. Okay. Now this is not a new idea. This is what people normally do, except that the way we do it is we do it such a way that our compactified autonomous system has actual equilibrium points or limit cycles. So the typical approach would be to do exactly that, add an extra variable. Okay, so you could, I'm gonna tell you what the standard approach does. So if you have x dot is equal to f of x lambda of RT, you introduce a new variable, which is u equals RT, and then you rewrite that thing as a set of two equations. Okay, so now this second set of equations is autonomous, obviously, but the problem is that it doesn't have any equilibrium solutions or limit cycles again, because R is greater than 0. The rate is greater than 0 when you have rate-induced tipping. So what compactification does, it uses a similar approach, but what it does, it sort of does a slightly different extra coordinate and a different additional equation, such that this extra equation introduces real equilibrium points. So you turn a non-autonomous system into an autonomous system with real equilibrium points. So if people would be sort of interested in this type of situation, I can give you a simple example that you can use as homework and work it out. So I'm going to now, for a moment, go and show you. Now, this is a PhD thesis of one of my students. Can you see it? So Paul O'Keefe wrote his thesis on the interaction of rate-induced and bifurcation-induced tipping in ecosystems. Okay, this is from 2019, and you can find it through Google Scholar, or this is on our UCC website. Now, if you go to chapter 7 of his thesis, just bear with me for a few seconds here. There we go. Okay, so he sort of look at that general idea of compactification here, and you will see, so he derives the extra equation. This is his ecosystem model. It's a plant herbivore system taken from a paper by Martin Schaefer, and his additional equation, looks like that. Okay, it's not a simple situation where S dot is equal R. It's a different equation, and this has equilibrium when S equals ±1. So S equals to ±1, where you get equilibrium for this equation, here corresponds to time being negative and positive infinity. So what you do, you have this situation where these lines, you will see these pictures in my talk next week. These lines are the frozen system equilibrium solutions. So this is one attractor, this is another attractor, you see. So here you track this guy. At the critical rate, you do something funny because you continue along the unstable state. And above the critical rate, you don't go to infinity like in my simple example, but you go to another attractor here, which is all the herbivores disappear and go to 0. So this is the non-autonomous picture. It's almost impossible to sort of capture this instability here in any way. But when you compactify, you sort of bring negative and positive infinity time and that at those infinities, you have this autonomous dynamics with equilibrium solutions. And then you can represent R tipping in the non-autonomous system as a heteroclinic bifurcation from the stable state in the past to the saddle state in the future. This is this green trajectory. So you can transform an R-tipping problem to a heteroclinic orbit problem in a compactified system. This compactified system is very easy. You can actually take these equations and you can find about R-tipping by computing the unstable manifold of that attractor from the past. An attractor in the past becomes a saddle when you compactify, because it's got this unstable direction due to S, due to that extra time dimension. It's attracting within the plane, but it's unstable here. And then you shoot with the unstable manifold. And you see, once you go to this continuation of that attractor, which is tracking, then you go to a different attractor in the future, which you R-tipped. And then you can try to look for a critical rate when you connect to something in the future which is not attracting, and that's a special heteroclinic connection. Okay, so this idea of compactification and the decaying inputs that underpins a lot of my research on rate-induced tipping, because we can make rigorous statements and we can also analyze examples in a very elegant way. So if you have some sessions in the afternoon and people are sort of interested in this type of things, you could program this simple system, and the equations for P and H are given above here, and sort of try to compute unstable manifold of that saddle equilibrium and then see if you can detect R tipping, but this type of approach. Okay, you will see a lot of other pictures in Paul O'Keefe's thesis that does the same approach here. It's a very short chapter, so be perfect for an hour exercise classes if you have anything like that planned or you'll be interested in that. So I think at this point, it's a good point to stop maybe, and to summarize what I've done. So I gave you a bit of an overview of dynamical systems, different type of dynamical systems are where we live here with our approach. I discussed this very simple example that has both bifurcation-induced tipping and rate-induced tipping. And you actually, in this simple example, are able to figure out both of them analytically. Okay, and then that required me to make two important assumptions. One is a linear ramp for the input. The other is a special structure of that system on the right-hand side. And in the third part, I try to generalize it so that the honest assessment is that we can't really do a lot for arbitrary inputs. However, if you assume that the inputs decay to infinity, to constants at infinity, and that makes a lot of sense, the system's at some state, a disturbance comes, however complicated, and then goes. So it settles back to something constant. Okay, this is the philosophical idea behind it. And then you ask, where is the system after the disturbance? Has it sort of adapted to the disturbance, or has it moved to a different undesired state? Now, if you have that setting, then you can make a lot of progress here. Progress in terms of using compactification, and again, trying to reduce an R-tipping problem to this global heteroclinic orbit problem in the compactified system. Okay, so I think this is all. Thank you very much for your attention. If anyone has any questions, you can always email me. I'll sort of be around a little bit next week, definitely for my own talk, but I'm slightly out of sync in terms of timing here, and I also have to teach and do other things. And I'm happy to answer any emails. And if people would like to have a go at this simple example, and if you can't find the link to the PhD thesis by Paul O'Keefe, I can email this to Partha later on, and he can share it to anyone who is interested. Thank you.
Can I ask a couple of questions? Oh, I have one question. Can I ask? Do we have time?
Sebastian, you have time, so we will have a couple of questions.
Yeah, I do have the time. Yeah, go ahead.
Yeah, thank you very much. That was really, really interesting to learn about this R-tipping and very elegant, simple mathematics as well. So I'm curious, so will at this critical rate, do we experience this critical slowing down like we find with other bifurcation points?
Yeah, so I myself haven't done any work on the early warning signals for rate-induced tipping, but other people did. People like Jan Sieber and Paul Ritchie have a paper about rate-induced tipping with noise, and you can see some of that. So maybe if I can, yeah. It's a tricky situation, right? So let me just see if I can give the best answer I can. Yeah, I'm gonna go back to this. So you see what happens here is that these plots are for different but fixed rates. Okay, so now it's sort of difficult to tell, but you can see that you have a stable line and unstable line. Okay. So if the rate were to drift, in this case, towards the critical rate, these two lines get closer to each other. As they get closer to each other, this one slowly loses stability. As it loses stability, then you again expect a different response of this line to noise. You expect that you're going to deviate further from that line, and then autocorrelation is going to increase, and also the standard deviation of the sort of disturbances, or when as you move away from the trend, you're also going to have an increase in that. But of course, it's a bit different, and this is a very special example. In general, there is some loss of stability, and there should be a clear early warning signal, but I don't think that people agree on what the clear early warning signal is for this rate-induced tipping. I think some ideas you can try to convey, but things become a bit different. And again, there are examples of rate-induced tipping where you don't have a clear-cut threshold, like this unstable line. And I should say that there are those special examples of rate-induced tipping actually do not correspond to any bifurcations of pullback attractors. And that's where there is a bit of a limitation on using pullback attractors alone. Okay, so I don't have a clear answer to that, and we don't have a very nice way of saying yes, you will expect this and that type of early warning signal.
Thank you very much.
Hello. Yeah.
Hi.
So I have one question. In the non-autonomous system, we have two parameters, lambda1 and lambda2, which are both dependent on R. And R is the parameter which is this for the slow scale, basically.
Yeah, it's a rate parameter. It tells you how fast you vary each of these parameters.
Okay, so in case, suppose we have R1 and R2. Let's say lambda1 depends on R1t, lambda1 is a function of R1t, and lambda2 is a function of R2t.
Yes.
Then how this compactification works?
Okay, so first of all, compactification works when lambda is a function of time, but such that as time goes to positive and negative infinity, then lambda tends to a constant. That's important, right? And so it wouldn't work with a linear ramp. And now what I described here would also be a compactification approach that works when you have one of these lambdas varying over time. If you have more than one vary over time, you can compactify the problem. Okay, still there is no problem with doing that, but you have to be careful when you choose the compactification, because you have to choose the compactification to the slowest varying lambda component.
Okay, so will it be like a two-dimensional, and then it will extend to a like I have to choose only one parameter?
No, that's the whole beauty of that. That's the whole beauty. That lambda can be 1000-dimensional, but you only add one equation for the compactification. So you take 1,000 different lambdas that do exactly what you do. You check which one has the slowest exponential decay.
Okay.
And then you design your compactification for the one with the slowest. The problem is that you cannot compactify faster than the decay of lambda, because you would lose differentiability at infinities. And this is a lot of technical problems. There's a whole paper about compactification. I don't want to go into the details, but I can send you the link to that paper, right? And that discusses these things. As long as you take the component of lambda that decays slowest and you design your compactification for that component, it will automatically work for all the other components of lambda. And you always add only one equation. It is a bit like magic because, you know, take this example, very complicated lambda. You may need to generate this lambda with, say, 1,000 of extra ODEs. Yet, when that lambda decays to a constant, you can fix the problem with just one extra simple equation. Yeah.
Thank you very much.
Hello, sir. Sir, if R tends to 0, can I say that R tipping tends to B tipping? Or is there any relation, conversion in between R tipping to B tipping or B tipping to R tipping?
Okay, so can you just repeat a bit slower the first part of your question?
Means if R rate tends to 0 or rate is very less, can we say that R tipping goes to B tipping, bifurcation tipping?
Yeah, so that's, I'm gonna sketch something new here for you, okay? And if we still have the time to do that, so let me just see. Yeah, okay. Let's just look at this.
We have time.
Yeah, all right. So this is lambda, okay? This is some state of your system. Let's say I'm going to plot some equilibrium solutions. So let's look at some node bifurcation, which is tilted. Like that, okay? So now I have two equilibrium branches, stable, unstable. So in the frozen system, this is attracting, this one is repelling, like so, right? And now I increase lambda over time. When my rate is very, very slow, I do this. I sort of track this one, and then it finishes and I jump to some other state, okay? However, if I go very, very fast here, I can deviate too much and I can jump earlier because of R tipping. So in this situation, this is large R. So larger R, and this is smaller R. Okay. So what you have, if you go very fast, you're going to have rate-induced tipping because of that tilt. Okay, and this Bayesian instability idea, which also is described, I'm going to describe in my talk. Then if you go a bit slower, you're going to sort of move, you're going to stop R tipping and you're going to move towards B tipping. So in some situation, by changing the rate, you can go from rate-induced tipping to bifurcation-induced tipping. And these examples, they come up a lot in the ocean circulation models, where people think, okay, you have this bifurcation, so you have to cross this threshold to have tipping point in this system. But in addition to having B tipping, the system is very sensitive on how fast you go. If you go towards this point too fast, you can tip earlier than you expect due to rate-induced tipping. I don't know whether that helps or answers the question, but I hope it does. So did it answer your question?
Yes. The student says yes. I have one last question, Partha, if it's still possible. Okay. I have one question. If I had only time series data and I observe a tipping, is there a way to distinguish R tipping from B tipping?
Yeah, this I don't know how to do it. That's the honest answer. You know, I'm not going to beat about the bush. Yeah, so that one way of trying to distinguish what's going on would be relating to the first question, whether there are any early warning signals for B tipping and R tipping, and whether are there different early warning signals. and try to analyze the time series for the early warning signals. Now, of course, we know that the early warning signals, they are very useful, but you cannot guarantee that they will appear. Okay? And sometimes you see them, sometimes you don't. But the only sort of way I would approach that problem is to try to understand, are there different early warning signals for different tipping mechanisms? And can I detect any of those signals in my data and maybe speculate a little bit whether what I see is rate or bifurcation induced tipping. Yeah, so that's, I know this is not a very promising answer, but this is how I see it at the moment.
Thank you very much.
I have a question regarding, like you talked about slow fast systems, right? So
all right, yeah.
I have a system where lambda is my bifurcation parameter, and then lambda crossing 0 is bifurcation. And
Yeah.
suppose in some way I can split lambda into two components, like alpha minus beta is my lambda, and something like alpha is varying at a different rate and beta is varying at a different rate. Like whenever alpha equal to beta, I get bifurcation. Then like now, like if beta is varying faster than alpha, I get bifurcation. So do you call this rate induced tipping or bifurcation induced tipping?
So I'm not sure what we are describing. So I try to maybe sketch something for you, okay, and then see if this is what you have in mind, just so that I understand your question better. So we have a situation where we have a problem. Okay, it depends on two parameters, lambda 1 and lambda 2. Let's say this is your A and B, right? And then you have a two-parameter bifurcation diagram, and you can have different bifurcations. So you have a saddle node bifurcation here. This is a curve of saddle node bifurcations. Okay, here we have two equilibrium solutions. Here we have 0.
Okay.
Okay. Now what you're talking about is this is my frozen system bifurcation diagram. If I fix lambda 1 and I increase lambda 2, I eventually have a saddle node bifurcation. But where that saddle node bifurcation occurs will depend on how I fix lambda 1. Okay, in this picture. So now generally you have a high dimensional parameter space. It's not just 2, it can be 3, 4, 5, 10 dimensional parameter space. So what you talk about is you talk about the path in the parameter space. So I can think of different paths through the parameter space. Let me just pick this simple path here, like this. Okay, so this is path number 1. Now, there is no bifurcation induced tipping along that path because I never crossed the curve of saddle node bifurcations, right? However, I could have rate induced tipping here along this path. If I choose a different path, this is path number 2. Okay, what happens here? You can guarantee that there will be bifurcation induced tipping because this path crosses. So you see, I'm changing both lambda 1 and lambda 2 at the same time, but maybe at different rates, right? This is what's going on. Along that path, there will be bifurcation induced tipping because I eventually cross the bifurcation, however slowly I go.
Yes.
But that doesn't exclude the possibility of rate-induced tipping happening here before you actually reach the bifurcation. So that links to this picture, okay? Before my parameter reaches the bifurcation value, it actually rate tips earlier. So now, how do I figure out whether I have rate-induced tipping along the blue path or even along the red path? So I would pick this point here. This is my starting point in the parameter space. And I'm going to check all the other points in the parameter space that will give me rate-induced tipping for this instantaneous switch. And I say for this, I end up with this region, which is gray. Okay. So if I switch instantaneously from this parameter setting to any parameter setting here, I'm going to have tipping. And this is what we call Bayesian instability, Bayesian or threshold instability. Now, I'm not going to explain in details what it is. It's going to be in my talk next week, but you can actually get an idea in the parameter space, like you're talking, 2 or 3 parameters. You can map out bifurcations for B-tipping, and you can also map out a Bayesian or threshold instability for rate-induced tipping. So if I start now with the red one, I can ask myself, do I have a Bayesian instability along that path? And it may turn out that there is here Bayesian instability. If so, then you have a danger of rate-induced tipping before you reach the bifurcation. So that's the way to analyze it. And I'll be talking about it more next week. Does that answer the question?
Yes, like I'll wait for your second talk, but actually I need a more like clarification. Like, say along the path 2,
Yes.
you are getting bifurcation induced tipping when you vary lambda 2 faster than lambda 1. It's like above, like rate of change of lambda 2 should be greater than rate of change of lambda 1, right?
Yeah. So at the moment,
In
the way
that
I
sense,
yeah.
do you call it rate induced?
No,
Bifurcation?
no, because it has nothing to do with how fast you go. You can, so this red line tells you that you vary lambda 2 faster than lambda 1 because of the slope.
Yes.
You see?
Yes.
But you know, it doesn't matter how fast you go. So let's say lambda 2 goes twice as fast as lambda 1. And you only worry about the rate of lambda 2 because lambda 1 goes twice slower. No matter how slowly you vary lambda 2, you always have bifurcation induced tipping here. So this is always B tipping. It's not rate tipping. It doesn't depend on the rate, you see? So there is something like, there's something funny about the question. It actually doesn't matter. You know, your starting point is not which one varies faster than the other. Your starting point would be what is the resulting path in the parameter space? And does that path cross a bifurcation, which is a dangerous bifurcation, or does it not? If it crosses a bifurcation, then you have B tipping. But what I was trying to say is that if lambda 2 varies too fast, you can actually have tipping before you cross that bifurcation within this red region here. So you go, slowly, then you tip. But if you go much faster, you can go here, and you can R-tip already here before you cross a bifurcation. So the rate-induced tipping has to do with the fact that you really cross a bifurcation, okay, or not. And to make things more complicated, if people really want to, consider this. And this is going to confuse you a lot, but I think it's a good picture to leave. Sometimes it's good to confuse people a little bit so they think about the problem. Look at this situation. This have 2 bifurcations, saddle node 1, saddle node 2. And it's a matter of how you define rate-induced tipping. But if you start here and you go slowly, okay, slowly, you're gonna go down to this state. So this is when R is slow. When R is fast, you're gonna go like this, you're gonna dip, but then you're gonna rescue yourself, okay? So we would call this rate-induced tipping in the sense that your final state depends on the rate at which you go. Here, as you cross that saddle node bifurcation, your final state doesn't depend on the rate at which you go. Okay, so as long as your final state doesn't depend on the rate, then you don't have rate-induced tipping. If your final state here depends on the rate, you have rate-induced tipping. I hope that helps a little bit.
Yes. Okay. Thank you.
One question I would like to ask. In that diagram you drew of the Bayesian instability.
Yes.
I'm not sure if this is the correct question to ask. Does that region of instability depends upon the parameter path or rate? Like, is it dependent upon some parameter?
Yeah.
The region of instability.
So this Bayesian, you talk about these pictures, correct?
Yes, the shaded part, yes.
Yeah. So that depends only on the initial point on the parameter path. Okay. And it's actually done for infinite R. So you Bayesian instability, Bayesian or threshold instability, it's a property where R tends to infinity. You go infinitely fast. So you see along this path, there is no bifurcation. You don't cross any bifurcations. So when you go slowly enough, nothing will happen. You can guarantee that because there are no bifurcations, correct?
Right.
So in the limit of R going to 0, you don't have any surprises. Do you know that you're going to follow your moving attractor? And this Bayesian threshold instability which I did is for the situation when R is infinite. You have an instantaneous switch from this set of parameters to any other set of parameters here. If you do this instantaneous switch and you go to a different state, then you have Bayesian or threshold instability. So this gray region depends only on the initial point on the parameter path. And it tells you that every path that connects this initial point in the parameter space to some other point in the gray area, there is a potential for rate-induced tipping, provided that you change R fast enough, so you change lambda fast enough. And what fast enough is, you don't know. You know that infinitely fast will give you tipping, infinitely slow will not, and that critical rate is somewhere in between. And the goal of this whole study is to find where that critical rate lies. And you can do it numerically by shooting, or you can sort of do some more clever techniques, which I mentioned briefly earlier.
Okay. Does that mean if I go through path 2, if I start from that red dot, I can get some other region of Bayesian instability, which...
That's right. So because the path crosses a bifurcation, does not eliminate the possibility of having Bayesian or threshold instability that gives also rate-induced tipping.
Okay.
And this is the example, you see. So now I'm having a path that crosses this bifurcation, right? So my lambda changes from here to there, and there's a bifurcation right there. So there's no bifurcation right there. So if I go slowly, I'm going to have bifurcation-induced tipping. But if I go too fast, I'm going to have rate-induced tipping before I have a chance to have bifurcation tipping. Because there is Bayesian instability on that path due to this attractor here not being the Bayesian of stability of its continuation here. This is in the Bayesian of some other attractor. So this guy from here is outside of the Bayesian of that guy.
So in the example we considered, the lambda one was not the bifurcation parameter in the example during the talk. Lambda...
Yes, in the example during the talk for the rate-induced tipping, lambda 1 was not a bifurcation parameter because let me just check because I have all these papers flying here and I forgot which was lambda 1 and lambda 2. Oh yes, lambda 1 is not a bifurcation parameter.
But
okay,
here we are... Yes, but here we are considering that lambda 1 is the bifurcation parameter, although the transition is happening.
No. I'm going to sketch the bifurcation diagram now for the system which I did earlier. Okay. So now this is a bifurcation diagram for the example which I did earlier. Okay. So now I have lambda 1 and lambda 2. Remember, the sudden node bifurcation occurred when lambda 2 was 0, and it was independent of lambda 1. So let's lambda 2 be equal 0. This is the line of sudden node bifurcations. Okay. So now I have 0 equilibria here, and I have 2 equilibria there. Now I use 2 different paths here. For bifurcation-induced tipping, I varied lambda 2. Okay, so for B tipping, I got this. I fixed lambda 1 to 0. Okay, so it's lambda 1 equals 0. I use this path. So what I was decreasing lambda 2. That was my path number 1. Okay, but to demonstrate rate-induced tipping, I fixed lambda 2 to 1. This be 1, and I increased lambda 1. So I used a very different path. This was my path 2. All right. So yes, I have two parameters, but really you don't get a bifurcation when you vary lambda 1 on its own. So I use one path here for B-tipping, one path there for rate-induced tipping, so I don't cross any bifurcation. But you can imagine that you do a third path, which goes like that. Path 3. And that links to other questions when you vary both lambda 2 and lambda 1 simultaneously. And then you can vary them at different rates. Okay, if one is much faster than the other, you'll be like this or like that. But take path number 3, that gives you both rate-induced tipping if you go fast enough, and bifurcation-induced tipping because you do cross this bifurcation.
Okay, yes, thank you.
Okay, so I'm just going to write it for clarity. So this was for demonstrating B-tipping, and that path was for demonstrating R-tipping. And like the whole point is, maybe I didn't articulate it very clearly, that if you look at this parameter spaces, and we have questions about it, and paths in parameter spaces, some special paths have only B-tipping, other special paths have only R-tipping. But generally, you know, in real situations, you will have parameter paths that don't go like that. They will go like here, and then you may have a combination of bifurcation and rate-induced tipping. And this is what the PhD thesis of Paul O'Keefe is about. And he also has a paper in the Science Journal on Applied Dynamical Systems where he describes this interaction. But the way to think about this in terms of different paths in the parameter space, and saying, if I choose a path, do I cross a bifurcation, which is dangerous and gives me sort of discontinuity in the branch of attractors, or do I not? If I don't, do I have threshold or Bayesian instability along my path? Because look, if I showed you that path at the beginning of the talk, you might think nothing can possibly go wrong along that path. I'm away from the bifurcation. I never crossed the bifurcation. What could go wrong? But it goes wrong because somewhere here, this point has this Bayesian instability region. So if you go from here into that region, you may have R-tipping. Okay, and I think what Paul O'Keefe's thesis does is trying to explain this Bayesian instability idea and Bayesian instability regions and map them out in some examples to demonstrate how these things come about.
Thank you, sir. This is very interesting. Thank you.
I hope that clarified some of the answers. But you know, if you still have questions, I still have some time. You can go ahead if it's not clear.
Any more questions? Anyone is having any question? Those who are attending it online. Okay. So Sebastian, I have one question. When you let's say you have an alternative stable state. Okay, and then you are following the third path. You have
Yes.
path one. You have path one, which is just for B tipping. You have path two, which is for R tipping, and you have a path three, which is both for B and R tipping. And now the framework that you have used, it is having just one stable and one unstable state, right? Now let's say I consider this S-shaped bifurcation curve that we quite often consider while talking about B tipping. So you are in such a parameter space where you have an alternative stable state, and then you follow the third path.
Yes.
Then what is going to happen?
Okay, so if you follow the third path, okay, if you go slow, so let's just go back to that picture, okay? So you could follow path number 3. If you go slowly, so the first question is, does that path has a Bayesian instability? And let's say yes. So now this is the starting point of the third path with my pencil, and I'm gonna say, okay, that has this Bayesian instability here. Okay, there is no point going past the bifurcation because it only makes sense when there is no bifurcation. So now I'm going along to path 3, starting from this point. This starting point has this Bayesian instability. If I go slow enough, I don't worry about that basic instability because there is no rate-induced tipping. Now I cross the bifurcation and I'm going to B-tip to the alternative stable state at this point, okay? This is what's going to happen if I go slow enough. Now, if I go faster, at some point, I'm going to have rate-induced tipping much earlier somewhere here because my rate is too high. It exceeded the critical rate for rate-induced tipping. And I'm going to go to an alternative stable state much earlier here along the path and due to rate-induced tipping. So if I now never reach the bifurcation and I go with the same speed, I still tip to the alternative stable state because of rate tipping. This bifurcation is irrelevant because I already have rate-induced tipping here. And this is this example. I have a bifurcation here. If I go slowly, I go to an alternative stable state. But if I go too fast, I go to my alternative stable state earlier before I even reach the bifurcation. So by going fast enough, you can have rate-induced tipping, and then this bifurcation is irrelevant. Whether you have this bifurcation here or not, it's irrelevant. You're going to have rate-induced tipping to the alternative stable state. So that's basically, did I understand the question all right?
I have now the second question. So let's say I add noise in such a system.
Yes.
Okay? Then if the noise strength is a little bit stronger, then obviously before I reach the tipping point, I will cross the potential barrier.
That's right.
And
okay, so a couple of comments on this one, okay? Comment number one is that a lot of systems that have tipping are not potential systems, okay? So you have to be always very careful about crossing the potential. Now, when you read these papers by Martin Schaeffer and other people, you know, they use potential systems because it's easy to illustrate ideas. But typical dynamical systems are not potential systems. So you cannot write a potential for a system like that. So it's not always so easy to see the potential. But when you add noise to the third path, then you're talking about the situation which is more complicated because you have an interplay between rate-induced tipping, bifurcation-induced tipping, and noise-induced tipping. And then the question is which one happens first, okay? So that will require some analysis and thinking about. Okay, so if I take the noise out of that equation, then I have a pretty good idea of what's going on, and we have a paper about it. If you add noise to the mix, then you talk about the interaction of 3 different tipping mechanisms, and that would require some analysis to answer this question. So maybe you can give it to a student, you know, to analyze it, or maybe be part of their PhD. I don't know, something like that. If you have a good system.
thank you so much. So if there is no more questions, then let us thank Sebastian for this. Thanks again, Sebastian, for this wonderful talk. And we are looking forward to your talk next week.
Yeah, thank you guys very much. You know, enjoy the rest of the workshop, and I see you next week. Yeah, now I'm off to teach some of my own students. Okay, bye. Thank you.